We previously established that for a very small numerical example, the mean of the population was equal to the mean of the sample means. But now let's establish that in general. If we have a population and we examine some parameter x, that in the population assumes the values from x1 all the way up to x sub capital N, where capital N is the size of the population, then of course the mean of the population is equal to the summation of x divided by that capital N. If we break this population into samples of size n, then the first sample of size n might be all of x1s, all the way up to terminating with x1, because when we create our samples, we are allowing for replacement. Now, the next one might have all of x1s also, except for the first one, which could be an x2. The question is, how many of different samples could you generate, each one being distinct from the others? The answer is familiar from our earlier problems on license plates. If you have a license plate of 4 numbers, then how many different license plates of 4 numbers can you build? The first one can be 10 different ways, and for each of those, the other one can be 10 different ways, and they can all be 10 different ways. So you can end up with 10 to the 4th different license plates. Similarly, if you're taking 3 letters out of the alphabet, the first one could be 26 different ways, the second one 26, and the third one also 26. So you get 26 cubed different ways. Here we're taking a population of n, and we're taking them n at a time, small n at a time. So the question is, how many different samples can we get? Just as with the license plates in the alphabet, it's capital N to the small n power. Now let's examine this table. This table will then have this many rows in it, and it'll have this many columns in it. And of course, the last row will be xn, 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 all the way up to xn. Now I want to ask the question. If I summed each of the entries in this table, then what would that sum be? First, let's establish how many entries are there in the table. There are n columns and capital N to the small n rows, so it is a table, it is a rectangle, if you will, length times width, so the number of entries is small n, the width, times the height, capital N to the n power. Now I want to know how many of those entries are going to contain an x1, and how many are going to contain an x2, and similarly, how many in x3, and all the way up. Let's examine the role of x2. When we start to put x2 in the table, first there will be a complete row of x2s. Then the first column will be replaced. When we start to put x3 in the table, first there will be a complete row of x3s. Then the first column will be replaced by something else. Therefore, the x1s, x2s, and x3s, all of the x's are present in the table in an exactly equal pattern. There are an exact equal number of x1s in the table, as there are x2s, as there are x3s. Therefore, the total number of entries in the table is divided by the number of different x's that you can have. And this is the number of each x's that is in the table. So the n's divide out, and there are n x to the n minus 1 of x1 and x2 and x3 and all the way up to capital N. There are an equal number of each of the x's in the table, and that equal number is small n, capital N to the n minus 1 power. Then, let's ask the final question for this part. What is the sum of all the entries in the table? If we added up all of the entries in this table, what would that sum come to? Well, let's ask how many x1s there are. There are n, capital N, n minus 1, x1s, plus n, capital N, n minus 1, x2s, plus all the way up to x sub capital N. So factoring out the common, the sum of all entries in the table small n, capital N to the n minus 1 times x1 plus x2 plus x3 plus all the way up to x capital N. We pair this with what we've already established about the mean for the population. Mu equals the summation of x divided by capital N. And these are the two results that we have generated in part 2. And we will carry these results present into part 3. And there we will show how these results generate the all-important conclusion that the mu of the population is equal to the mean of the sample means.